All right, welcome back, everybody. Today we're going to be moving into chapter 8. So we just finished chapter 7. Now we're going to do chapter 8, and today we're going to talk about arc length. And then next time we'll talk about surface area. Let me get the slides. This one should be shorter than the last two. So here's crossing my fingers, but this is a fun section. I actually like this section a lot. There's a couple things we got to review, but then the results are actually pretty straightforward, so that's kind of nice. All right, here's the overview. We're going to briefly recall one of the most important theorems in mathematics, in my opinion, the Riesz-Markov-Kakutani representation theorem. And I talked about this in my basically review lectures that I recorded for this class. This is not a theorem that you need to like have mastered or understand deeply, but it's a theorem that basically motivates why we even care about integration to begin with. That's why I like to talk about it. So we're going to review what it basically says. Then we'll talk about the arc length formula. Then we're going to talk about the notion of rectifiability. And one of the reasons I like this section is because it gives me an in to briefly talk about fractals, which are objects that I study. So um, my work involves fractal geometry, and I'm basically a fractal geometer that does analysis with fractals, in particular space-filling curves. So it's always fun when I can talk a little bit about my research and modern math research in a class like this, because these are the techniques that you build off of to do that type of stuff. So we'll briefly talk about fractals, and then we'll finish up with the arc length so far function, which really isn't that much more. All right, so this is the Riesz-Markov-Kakutani representation theorem, otherwise just known as the Riesz representation theorem, and it's this very complicated, detailed mathematical statement that you learn about when you take a graduate course in analysis. If you're getting a degree in mathematics, you will talk about this in a graduate course on analysis. Um, I'll read some of it, but basically it says this. Any positive linear functional that is nice enough uh, can be written in this form. That's really what it means. And this is the piece that you all know about. So this is basically an integral. It's an integral over some set or some region, some interval. It's the integral of a function. And this is basically dx. So dx, except instead of it being x, it could be some other function, mu of x. And what this result says, what this theorem says, is that any linear functional can be written as a Riemann integral as long as the as long as the functional is nice enough in some sense. All right. So why is this important? Because the big idea is what's in the box, and this is what I hope you can kind of take away from this complicated mathematical theorem. Basically, it says that the Riemann integral is our canonical measuring device. And when I say our, I mean the human race. I mean human beings as an existent, sentient entity in reality, in existence. Um, this is saying that we can basically use the integral to measure anything as long as the thing we want to measure has some nice properties to it. So, for example, if you want to measure volume or arc length, like today, or surface area, like the next time, or the charge of a particle, or risk, or probability, or efficiency, or accuracy, or class attendance, all these things, you can write that as a Riemann integral. So the integral is our measuring tool. It is the thing that lets us measure things. And it's one of the most profound creations by the human mind in human history. And the fundamental theorem of calculus is also connected to this, and that's actually one of the most amazing results in human history, in my opinion. Um, so when you work with integrals, what I want you to do is I want you to think of them as measuring devices. And you have to figure out what you're going to measure and how you're going to measure it. And that's a lot of what we do with integrals. We find something we want to measure, and then we figure out how we can measure it. And the integral will be our ruler. That's essentially it. All right? We're going to use it right now to find arc length. So the goal here is we will have an arc, or basically a curve, on the plane, and we want to know how long it is. That's it. That's it. So that's the goal here. So we need one definition to start. We say that a function is continuously differentiable if it is differentiable and its derivative is continuous. So it's a little bit subtle, but what we're saying is that you can differentiate the function, and that derivative is also, excuse me, continuous. Um, One little side note I put here is remember that if a function is differentiable at a point, then the function is also continuous at that point. But that does not mean that the derivative is continuous at that point. And a good example is square root of x. So hopefully your Calc 1 professor talked about this a little bit, but let's compute the derivative of square root of x. So f prime of x is 1 half x to the negative 1 half, which is 1 over 2 root x. So notice here, this function is not defined at x equals 0, but this function is. So our function f is continuous at 0, at least continuous from the right. So our function f is continuous from the right at 0, but our derivative is not continuous there. So just because your function is continuous, that does not mean that your derivative is continuous. All right. So we are requiring something very specific here. We are requiring that not only are our functions differentiable, but the derivative is also continuous. Okay, that's one thing we're requiring here. All right, so here's the setup. If we've got the curve of a continuously differentiable function y equals f of x in the plane R2, defined over an interval a to b, how long is it? How long is it? So the setup is pretty straightforward. Here we go. Here's the interval a to b. This is the plane R2. We've got a curve. Maybe our curve looks like this. Oops, too far. Let me go back. Okay, my question is, how long is that curve? That's it. I want to be able to know how long it is. Well, um, like I say here in the next bullet point, if we could just pick this thing up off the screen and straighten it out and then hold it up against a ruler, then we could measure how long it is, right? It would be easy to measure if we could just literally pick it out, straighten it out, and then put it against a ruler and go, oh, okay, it's that many centimeters, right? Then we could measure it. But we can't do that. We can't do that. This is a curve that's just been sketched on the plane or on a piece of paper. It's just sketched there. We can't pick it up. But we would really like to be able to measure how long it is, right? How do we do that? Well, we're going to approximate it. We're going to approximate it. So like we talked about in 7.7, we can get a pretty good approximation of a function with straight lines. This is a first order approximation. So what we're going to do is we're going to take our curve, which is this thing right here, and we're going to subdivide the interval a to b into a bunch of subintervals. It sounds kind of familiar, right? Then we're going to create a first order approximation of the function on each interval. So on this interval, this line right here, actually let me do this. Here we go. This line is the approximation of the curve, and then this line, 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 and then this line. And we got an approximation of the curve. It's just kind of jagged and straight. It's not very exact, right? But it is an approximation. And the good news is that straight lines are easy to measure with a ruler. We just need to find their length, right? We just need to find their length. So what is the length of each one of those segments? I want you to ponder that for a minute. What is the length of each one of those segments? How could we find it? What could we use? Any ideas? All right, say something out loud. What could we use to find the lengths of those line segments? All right, so if you were thinking distance formula, you were correct. The distance formula, which is just the Pythagorean theorem. So we can use the Pythagorean theorem to find those lengths. And what we're going to do is we're essentially going to create a right triangle like so, where this is delta x and this is delta y sub I. That'll depend on where we are, delta y. And then once we know that, we can find this length. Maybe actually what I'll do is I'll call the length L sub I. So we know what delta x is. We chose our integral to have, I'm sorry, we chose our intervals to be the same length, right? So they're the same length delta x. Now, delta y will depend on I, because as you can see, the height of this triangle is very different from the height of this triangle right here, right? This triangle right there. So we are going to have to, delta y is going to be different depending on I. Okay, so here is the distance formula. What is L sub I? Remember I called that L sub I? It's, it's this, xi minus 1 squared plus yi minus 1 squared. In other words, it's delta x squared and then delta y sub I squared. And that is the length of each one of those approximating line segments. So if we want to get an approximation of the curve, oh, wait, sorry. Hold on 1 second. Oh, yeah, that's right. If we want to get an approximation of the whole curve, then we would have to add up all those line segments, right? But there's one caveat here, and the caveat is this y sub I, delta y sub I. That depends on the interval, and we don't want it to have to depend on the interval. We want it to be something that is not, how do I put it? We don't want to have a second variable. That's really what's going on here. So this is only single variable calculus. We don't have the tools of multivariable calculus. We need to eliminate one of these variables. We can't talk about both x's and y's. We can only talk about x's. So we need to re-express delta y sub I in terms of delta x's. And this is where there's an important theorem from Calc 1 that comes in, the mean value theorem for derivatives. So if you took me for Calc 1, we talked about this at length and I emphasized how important it is. And I gave you a little story about how I had to talk about this when I was getting hired as a TA once. So this is the thing. Since f is differentiable on each one of these subintervals, f is differentiable here, and it's also continuous on each one of these subintervals, the mean value theorem for derivatives applies. And what the mean value theorem says is that there is a point, x sub I star, in that interval where delta y is equal to f prime x sub I star times delta x, right? Or in other words, remember the mean value theorem says if your function is differentiable on that interval and continuous on that interval, then there's a point in the interval where the instantaneous rate of change is equal to the average rate of change. That's what that theorem says. So what that means is that we can write delta y sub I as f prime x sub I star times delta x. This is how we're going to eliminate our variable y. That's how we're going to eliminate it. All right, now let's go and plug this in. So delta y sub I is now equal to this value instead. Now we can pull out a delta x squared from each one of those terms, and voila, we get that. There we go. So this is the length of each one of those things written in terms of just x's and f of x's, right? But f of x is not so bad. We have a formula for f of x, or f. We have the function, I should say. All right. Now we can write these L sub i's in terms of a single variable, and if we add them all up, we get an approximation. So the actual length of the curve that we're interested in is about the sum of each one of these linear approximations. All right, so let me pause here for a minute. I want you to look at that formula and look at the picture and just ponder it for a minute. Okay, so that's really what's happening, right? So the length is approximately the sum of those approximate line segments, right? Now what we're going to do is we're going to take the limit as n goes to infinity. That's an approximation, right? But if we increase the number of subintervals indefinitely, then the length will be equal to that limit if the limit exists. If the limit exists. So now we're going to push the number of subintervals to infinity. And if this limit exists as a finite number, then we've got the length. Ta-da! And that is where we get the arc length formula. So this is the formula for the arc length. This is the formula that you want to memorize, that you want to have in your head. And it's a really, really easy formula to derive. That's one of the fun things about this section. It's really not that hard to do. You just use the Pythagorean theorem and add up the results. All right, so here's the theorem stated in its completeness, in its entirety. Let f be a continuously differentiable function on an interval a to b. then the length of the curve on that interval is given by this formula, or this formula. It's the same thing. This is Lagrange notation. This is Leibniz notation. There it is. Now, before we talk about rectifiability, this is one of the reasons why the Riesz representation theorem is so important, because what we did was we used an integral now not to measure area, but to measure length. We just had to construct the function that would actually give us the length. And this is a lot of what happens when you use integrals. You have to come up with the actual function that is going to let you measure the thing that you want to measure. We wanted to measure arc length. So we found a way to construct a function that would tell us the length on some subinterval, and then we added up those lengths to get the total length. That is the process of integration. That's the process of integration. And you're going to use it for all sorts of applications, all sorts of applications. This is just one very specific application of it, and it's very cute. Okay, now let's talk a little bit about rectifiability. So this is an important idea, but the process of approximating a curve by a finite number of line segments is called rectification. Maybe you might think of like rectangle, for example. You're just using lines to approximate the length of a curve. Now, if the limit of this rectification is a finite number, then we say the curve is rectifiable. So in other words, if a curve has finite length, then it's rectifiable. If a curve does not have finite length, then it is not rectifiable. All right, so rectifiable means finite length. Why is this important? Well, there are many, many curves that are not rectifiable at all. And a good example is the Weierstrass curve, which I talk about in section 2.2 in Calc 1. That's when you first start to talk about differentiability and how it's related to continuity. And Weierstrass created this curve in I think it was the early 1900s, maybe late 1800s. He created this curve as basically the counterexample to the connection between continuity and differentiability. So this curve is it is continuous everywhere, but it is differentiable nowhere. I think I say that here. No, not yet. It's differentiable nowhere, but it's continuous everywhere. And what happens is when you zoom in on any piece of it, it just looks more and more jagged. So there's basically a corner at every point on the curve. But here's the thing, this curve is not rectifiable. It has infinite length. And this is kind of weird because it looks like it's constructed with line segments, but if you zoom in on any one of those line segments, you won't have a line segment, you'll have a corner. So even though it looks like it could be rectifiable, it's not. It has infinite length. But what's even weirder about this curve is, oh yeah, it has infinite length, but it has infinite length on any interval, any bounded interval. So give me an interval of any length that you want. Even like, even if you didn't want to go very far, maybe you just wanted to go from like here to here and just look at that part of the curve, the length is infinite on that interval. If you shrink it and do an even thinner interval, so you only have that piece, the length of the curve in that interval is infinite. So it's even weirder. It's not rectifiable and it's very, very weird. It's got infinite length for any bounded interval, negative epsilon to epsilon. Okay. Here I included the Desmos demonstration of it. I won't spend the time on it right now, but I encourage you to go look at that Desmos demonstration and just like try to zoom in on the curve and see what it looks like. Or maybe we can do it during the activity time, but I won't spend time on the lecture doing it. You can go explore that on your own. So another example of an interesting curve is the Koch snowflake, or the Koch snowflake. It's a curve that has infinite length, but it bounds a finite area. So ponder that for a minute. Think about that. The curve is infinite in length, but the area that it contains is finite. Yeah, very weird stuff. And these objects are still studied today. So like I said, like I do a lot of fractal geometry and research in fractals. These things are still studied to this day, active field of research. And we actually have some interesting info about this particular curve. For one, the area of the snowflake, this is just an approximation. You keep doing this forever and ever and ever. The area is 8/5 the area of the original triangle. So if you know the area of this triangle, you know the area of the snowflake. It'll be 8/5 times this area. That's it. Another interesting result involving rectifiability is the coastline paradox. This one's really fun to ponder. The coastline paradox is the statement that the coastline of a landmass is not rectifiable. So here's an example of Great Britain's coastline being rectified or trying to be rectified. So basically, what you do is you come up with a bunch of rulers and you try to measure the length of a coastline, and you get some number and you write that number down. And then you shrink the size of the ruler. So make the rulers a little bit smaller. And when you do that, the length of the coastline will increase. And then if you shrink the rulers a little bit smaller, the length of the coastline will increase even more. And as it turns out, as you keep shrinking the rulers, the length of the coastline keeps growing in size and it increases to infinity. So the length of the coastline of any coastline on the planet is infinite, but every coastline contains a finite amount of area, a finite landmass. Weird, huh? Interesting stuff. Then we can talk about fractals. So here's one of the more famous fractals. This is called the Sierpinski gasket. Um, and um, a lot of these fractals have interesting properties involving lengths and areas or volumes and surface areas and so on and so on. So this one in particular is interesting because the Sierpinski gasket this is an approximation to it, but what you do is you keep pulling out those inner triangles. And the end result at the limit, at the end of all of this pulling out of triangles is what is called the gasket, the Sierpinski gasket. And it turns out that if you were to add up the lengths of all the line segments that remain, it's infinite. It's infinite. So if you add up the lengths of all the remaining line segments, you get infinity. But if you tried to figure out what the area of the gasket is, the area turns out to be zero. Yeah, turns out to be zero. So here I'm basically pulling out a triangle, pulling out a triangle, pulling out a triangle. I'm removing area at each step. Well, if you add up the area at the end of all of this, it's zero. So this is an object that has zero area, but infinite length. Infinite length. And this is one of the reasons that the concept of fractal dimensions was developed, because we would like to be able to talk about what the dimension of this object is. For example, things that have finite area are two-dimensional. Things that have finite length are one-dimensional. But this thing has infinite length, so it's not one-dimensional. And I suppose you could say it's two-dimensional, but it has zero area. So it's almost like the notion of one dimension and two dimensions notions are not enough to talk about something like this. And so that's where you want to talk about, or you need to introduce the concept of fractal dimensions, fractal dimensions. And this one, the dimension of this one, oh shoot, I hope I don't mess it up. It's it should be log base 3 of 4, if I'm not mistaken. Oof, I gotta check. Hold on one second. I don't want to misstate it. All right, I apologize. It's log base 2 of 3. Don't tell my advisor. It's been a while since I've worked with this particular fractal. But the fractal dimension of it is actually log base 2 of 3. The reason those numbers are coming out is because the scale is 2 and the number is 3. So the relationship of this triangle to the big triangle is that you shrink it by a factor of 2, and then there's 3 that are left over after that. So in this case, we would say that the dimension of this object is log base 2 of 3. Right. I think of the Cantor set all the time, which is log base 3 of 2. So I always mix them up. Anyway, um, more on that later. If you're interested, I'd be happy to talk about fractals, but there's a time and a place, and let's move along and get back to Calc 2. All right, so we derived the arc length formula, and now we're just going to use the arc length formula to compute the length of this curve on the interval 1 to 4. At this point, there's not much to do except compute the derivative, plug it in, and then simplify. So let's jump right to that. Computing the derivative should be easy. It's a power function. We get that the derivative is 3/2 x to the 1/2. It's continuous on that interval. It's differentiable, or our function, original function is differentiable, so we can use the arc length formula. And here's the simplification. So this is the formula, and yes, this is a formula you need to memorize. You want to make sure you know this one. We computed the derivative. There's the derivative right there. And now we're just going to simplify. So we've got a pretty nasty, pretty complicated integral. We're just hoping that it simplifies at this point, right? So this simplifies to this. And this one we can actually deal with by using a u substitution. So we let u be this radicand. Then we get this, and we got to change our bounds. So we change our bounds. And now we've got an easy integral to evaluate. We can hit it with FTC2, and now we've just got a bunch of numbers, and then this is a simplification of that result. That's pretty much it. Okay, so one note about this I will say is simplifying these radicals is really the difficult part of these types of problems. So generally speaking, when you have an integral like this, at least in this class, you want to try to factor the radicand or do a substitution that'll make things easier. That's really what you've got to do. Maybe surprisingly, maybe not so surprisingly, whenever you have a radical of some stuff being added or subtracted, it makes the integration a lot harder. It makes the integration a lot harder. And I'm speaking from experience here because my research involves doing a lot of integration of distance functions. And remember, this is really just a distance function. It's the distance between the 2 points of those linear approximations. It's length, right? This is the length of those lines. And just by introducing that simple length where you have a radical involved complicates things immensely, And a lot of my research, I try to really avoid having to work with things like this, and try to come up with a distance function that is simpler to integrate so that I can get an actual number. So the simplification process is usually the more difficult part. Just want to give you a heads up about that. But here's an example of this one. So that is the length of that curve between 1 and 4. All right, now that we've got the formula, we can talk about the arc length so far function. And this is really just what it sounds like. It's just finding the length of a curve up to some point. And you can change that point and talk about the length as you kind of go along, like the area so far. So let's say we've got a curve of a continuously differentiable function f defined on some interval containing a. Then the arc length function, or the length so far function, is given by this integral. So this is just the length of the curve from a to x. And then as you let x vary, you get a different length. Okay? That's really what it is. That's pretty much it. It's just the arc length so far. Remember, we had the area so far function. Now we've got the length so far function. So similar to that. Moreover, by FTC part 1, we get this, that the differential ds is equal to that length times dx. And this is one of the reasons why, for any of you who've done calculus or like calculus-based physics, a lot of times they will talk about ds. ds is basically the change in the length of the curve. Because a lot of times when you're doing calculations, you don't really care so much about how the horizontal distance changes. What you care about is how the length of something changes, right? Let me give you an example. If I've got a particle that moves from here to here along this trajectory, I want to know the position and the velocity and acceleration and all that stuff of the particle based on where it is along the curve, right? Not so much based on how far to the right it's moved. I want to know how far it's moved along the curve itself. That's why this comes into play, because now you can talk about the change in the arc length versus the change in x instead. Again, we can talk more about that during activities if you've got questions, but just something for you to think about for the future. All right, and on that note, let's play. So I'm glad this one was a lot shorter. Again, thanks for bearing with me for the other 2 lectures. I know it can be hard to sit and listen to so much mathematics. I can listen to it nonstop, but I'll end it here so that you all can get along with your days, and I will see you very soon. And thank you again.